Welcome. Today, we're diving into the fascinating world of microoperations, the tiny yet powerful actions that drive the inner workings of computers. Microoperations are the basic operations performed on data stored in registers. They form the backbone of how instructions are executed in a computer system. By understanding microoperations, you'll gain insight into how computers process information at the most fundamental level. In this video, we'll explore what microoperations are, their types, and how they work together to execute complex instructions. Let's begin our journey into the heart of computer architecture. Microoperations are the elementary operations that occur within the CPU. They involve manipulating data stored in registers, such as transferring, adding, or shifting bits. Each instruction a computer executes is broken down into a sequence of microoperations. Think of them as the smallest steps a computer takes to complete a task. Without microoperations, complex instructions could not be executed efficiently. They are essential for the smooth functioning of every digital system, from your smartphone to supercomputers. Microoperations can be categorized into four main types: register transfer, arithmetic, logic, and control microoperations. Each type plays a unique role in processing data. Register transfer microoperations move data between registers. Arithmetic microoperations perform calculations like addition or subtraction. Logic microoperations handle bitwise operations such as AND, OR, and NOT. Control microoperations manage the sequencing and control of operations within the CPU. Together, these types enable the CPU to execute complex instructions efficiently. Register transfer microoperations are responsible for moving data from one register to another within the CPU. This is a fundamental operation, as most processing tasks require data to be relocated before any computation can occur. For example, copying the contents of register A to register B is a register transfer microoperation. These operations are fast and efficient, ensuring data is always where it needs to be for further processing. Arithmetic microoperations perform mathematical calculations on data stored in registers. Common operations include addition, subtraction, increment, and decrement. For instance, adding the contents of two registers and storing the result in a third is an arithmetic microoperation. These operations are crucial for tasks ranging from simple calculations to complex algorithms, forming the core of computational processing in the CPU. Logic microoperations handle bitwise operations on the data in registers. These include AND, OR, NOT, and XOR operations. Logic microoperations are used in decision-making processes, data masking, and manipulating individual bits within a register. For example, performing a bitwise AND between two registers is a logic microoperation. These operations are essential for tasks like setting, clearing, or toggling specific bits in data. Control microoperations are responsible for managing the sequencing and execution of other microoperations. They ensure that each operation occurs in the correct order and at the right time. Control microoperations coordinate the flow of data and instructions within the CPU, making sure that complex instructions are broken down and executed step by step. Without control microoperations, the CPU would not be able to function in an organized manner. Let's look at a simple example of a register transfer microoperation. Suppose we want to copy the contents of register R1 to register R2. This operation is written as R2 left arrow R1. The CPU uses control signals to enable the transfer, ensuring that the data in R1 is accurately copied to R2. This basic operation is used repeatedly in more complex instructions and is fundamental to CPU operation. Now let's see an arithmetic microoperation in action. Imagine adding the contents of registers R1 and R2 and storing the result in R3. This operation is written as R3 left arrow R1 plus R2. The CPU's arithmetic logic unit, ALU, performs the addition, and the result is placed in R3. This simple operation is the foundation for more complex calculations performed by the CPU. Let's explore a logic microoperation using the AND function. Suppose we want to perform a bitwise AND between registers R1 and R2, storing the result in R3. This is written as R3 left arrow R1 and R2. The ALU processes each bit, and the result is placed in R3. Logic operations like this are crucial for tasks such as masking and bit manipulation. Control microoperations are responsible for sequencing the execution of instructions. For example, when executing a multi-step instruction, control signals determine the order in which register transfer, arithmetic, and logic microoperations occur. This ensures that each step is completed before the next begins, maintaining the integrity of the operation. Timing is crucial in microoperations. Each microoperation must occur at the right moment, coordinated by the system clock. The clock ensures that data transfers, calculations, and logic operations happen in sync, preventing errors and ensuring smooth execution. Proper timing allows the CPU to execute instructions efficiently and reliably. The Arithmetic Logic Unit, or ALU, is the part of the CPU that performs arithmetic and logic microoperations. It receives data from registers, processes it according to the operation specified, and sends the result back to a register. The ALU is essential for all computational tasks, from simple addition to complex logical decisions. Every instruction executed by the CPU is broken down into a series of microoperations. For example, a simple addition instruction might involve fetching data, transferring it to the ALU, performing the addition, and storing the result. Each of these steps is a microoperation, and together they complete the instruction. Control signals are used to initiate and manage microoperations. These signals are generated by the control unit and direct the CPU to perform specific actions, such as transferring data or performing arithmetic. Without control signals, the CPU would not know when or how to execute microoperations. Microoperations are closely tied to the machine cycle, which includes fetch, decode, execute, and store phases. During each phase, specific microoperations are carried out. For example, during the fetch phase, data is transferred from memory to a register. Understanding this relationship helps clarify how instructions are processed in a CPU. The bus system in a computer facilitates the transfer of data between registers, memory, and other components. Microoperations rely on the bus to move data efficiently. For example, a register transfer microoperation uses the bus to send data from one register to another. The speed and design of the bus system directly impact the performance of microoperations. Modern CPUs execute millions of microoperations every second. Advanced designs use techniques like pipelining and parallelism to increase efficiency. By overlapping microoperations and executing multiple at once, CPUs achieve higher performance and faster processing speeds. Understanding microoperations is key to appreciating the power of today's processors. The instruction set architecture (ISA) of a CPU defines the set of instructions it can execute. Each instruction is implemented as a sequence of microoperations. The design of the ISA influences how efficiently microoperations are executed, impacting overall system performance and capabilities. To sum up, microoperations are the fundamental actions that enable computers to process data and execute instructions. They include register transfers, arithmetic, logic, and control operations. By working together, these microoperations allow CPUs to perform complex tasks quickly and efficiently. Understanding microoperations gives you a deeper appreciation for the technology powering our digital world. As technology advances, microoperations will continue to evolve, enabling even more powerful and efficient computing systems. Whether you're interested in computer engineering or just curious about how your devices work, understanding microoperations is a valuable foundation. Stay tuned for more deep dives into the inner workings of computers and digital systems.